Hi everyone, welcome again to the machine learning, intro to machine learning, Scikit Learn and TensorFlow workshop. Um, Thanks to Google for sponsoring us today with this huge room, lunch, breakfast, coffee. Um, so we'll do quick self-introductions with all the volunteers. So as you can see, we have a big team here who helped organize this event. I'm Kendall, and I work at a startup in Redwood City called YesGraph. And I used to live in San Diego, and I had a couple of friends from San Diego, also in the San Diego Python users group, who moved up here. So we started running these Python workshops, and that's how we got this event started. So let's do introductions. With you want to?
So I'm Catherine.
Catherine, you want to?
I'm Catherine. I'm a software engineer at Google on the Google Photos team, and I have a background in computer vision and machine learning research.
Hello, everyone. My name is Haley, and I work on Google Cloud Platform team, sales and partnership.
Hi, I'm Olivia. I'm a software engineer. I work on the Google Brain team and TensorFlow infrastructure.
Hi, I'm Kim. I know Kendall from San Diego Days Python user group. I do mainly Android development here at Google.
Hi, I'm Kavya. I'm a test engineer at Netflix, and I work with a lot of folks that do a lot of machine learning.
Hello, I'm Alan Domisi. I'm from the San Diego Python user group. I'm a software engineer, and I work currently with the lab at UCSD doing machine learning for bioinformatics.
Hi, my name is Karthik. I run the security team at a startup called Adapar. I write a lot of Python code.
Hi, my name is Micheline Harris. I'm one of your speakers today, and I am a data scientist at Microsoft, and I realize I'm in the belly of the beast. But I hope you will accept me. So at Microsoft, as a data scientist, I also do training in advanced analytics, and so I'm really excited to be here. I'm really honored to be here, actually, to be able to speak with about Scikit Learn. So.
I'm David Clark. I'm a data science consultant, and my background's in astrophysics, and I recently transitioned to careers to data science. I will be presenting the afternoon session on pandas and skflow and TensorFlow, and hope you find it enjoyable. Thanks for coming.
I'm Giri. I'm a principal architect with this company called Premise Data Corporation. I mostly write code, and I don't like Python.
Hi guys, I'm Vipul, and I'm a graduate student at San Jose State, and I'm just learning here, and it's great you guys all are here. Have a good day.
Okay, so if you have questions during the day, here are volunteers, so feel free to ask them. I think we have red name tags. Hopefully it's just just the volunteers. So we'll have a lunch break at noon, and then 1 to 1:30 we'll have a short math tutorial, and then 1:30 to 3:30 or 4 we'll have the TensorFlow tutorial. So Micheline will get us started here. So yeah, whenever you're ready. Yes.
So for folks who are having installation issues on Windows, you could try using Binder. I think Alan's mentioned it to a few people. I think it's a hosted solution where you can run your notebooks. I don't think you can save them there. You have to save them locally. But I think it's got all the tooling set up, both for TensorFlow and Scikit Learn.
What? Hi.
Don't you think it's a bit narcissistic, Michelin, that's having your pictures up there like that?
It's not, you're not being recorded. Don't worry. Are you ready to push that now? Yeah, I am. Yeah. Center me. I can join it. Oh wait, I am. Is it because would you? I got it. Okay.
Hi, good morning. I'm back. So, great. Now that you've met your neighbors, and you're all cozy, and we're all very cozy today, right? Because it's super crowded. Thanks for showing up, by the way. This is very exciting. So I hope you guys get a lot out of this. Hopefully you guys have a Jupyter system up and running with Scikit-learn. If not, and you have a neighbor that has it, maybe you guys can share. But it seems like most of you have that working, which is great. And the binder link should work. Like I said, it might get overloaded. It shouldn't. They said it wouldn't, but that's an option. And also, if you haven't joined the Slack group yet, I highly recommend you join that. Because it's a great place for you guys to ask questions to us and to each other. Do you need the link again? Or the Slack group is full? All right, we'll get that fixed for you guys and let you know when you can join. All right, so how many of you guys use, this is probably a silly question, use Python regularly? Great. How many of you do machine learning in Python regularly? All right, great. How many of you guys do deep learning in Python regularly? Wow, that's cool. I'm just curious because, that's the afternoon stuff. All right, so let's get started. Go ahead and if you're doing this interactively, open up the module. Let's go ahead and test your setup. So the 0, setup and primers. Okay, so you should have, hopefully it looks the same for you and me. So there's a module called version information. So if you pip install that, oh, I'm sorry. Hold on. Sorry about that. So if you scroll down to the code cell, it says pip install version information. This is the easiest way to test our install. It's actually a pretty nifty module, so I wanted to show you guys this module. So once that installs, then you can run the, I'm actually going to go ahead and introduce Jupyter Notebooks alongside this part and also throughout. So these are each, the gray cells are our code cells. Those cells you can modify. You can actually modify the text as well. It's just README, not README, Markdown. But you'll be interacting with the code cells. So to run a code cell, you put your mouse in that cell, click in that cell, and you hit Shift Enter or Shift Return, and that's the shortcut to running the cell. You can also go up to the toolbar up here, and there's a little run button. But we all love shortcuts, right? So there's actually a lot of shortcuts for Jupyter notebooks. And oddly enough, they're really similar to VI. I love it. It's like a throwback to the past. So anyway, hopefully, so I'm going to go ahead and do this. Shift Enter in that code cell. It's already on my computer, so that's great. I'm running mine locally, by the way, just so I don't take away any bandwidth from anyone. So hopefully, if you guys, see, I have TensorFlow in this. You guys might want to take that away if there's a problem with TensorFlow in your system right now. So I'm actually going to delete that real quick.
Does it matter if we're using Python 2 or Python 3?
So this should not matter between Python 2 or 3. The notebooks we tested on different versions, and they were compatible, and they ran on both versions of Python. So as long as it's Python 2.6 or above and 3.3 and above. Okay, so that's the test of this setup. Like I said, if it's just not working for you, we'll be having a couple breaks as well during this part of the workshop, and we can help you guys with that. So I apologize if it's not quite working. If you have a neighbor that can help you out or that has it working, that would be great if you guys could like pair up or buddy up. So. Does it not work? So if you're in the online version, like the cloud, you could actually do it individually. So just import, just shift enter in these cells right here. So import NumPy, shift enter, import matplotlib. Just make sure those don't throw any errors. Why do I have this open twice? All right, so I'm going to go ahead and push on, and we're going to open up the next notebook. So that's notebook 01, and it's our introduction, our machine learning 101, and really like basic introduction to scikit-learn. All right, so like I said, obviously you know this, but you're in a Jupyter notebook, and it's compatible with Python 2 and 3. And so I'm just going to plunge in. A lot of you, I mean, you guys are machine learning people, and that's why you're here. So you probably know this already. I just like to include, reminders for in case, terminology stuff or things to think about, right? So I really like, I don't know if you guys have watched Jake Vanderplas's presentation from PyCon last year. He did a really good one on scikit-learn, way better than probably I will do. But in his presentation, he said machine learning is, and we all know this, right? It's a subfield of AI. And those like algorithms in machine learning are the building blocks that can make in AI, like computers learn to behave more intelligently. And it does that by generalizing rather than just like retrieving data that is in a database system and stuff like that. And he actually goes on, I don't know if you guys, oh, you know what? I'm going to increase the size of this because that's always a thing in presentations. So you guys in the back can see this. All right, so he also goes on to say that it's about building programs with tunable parameters, which you guys, probably know about. Really like trouble, always interesting choosing the right algorithm, but it's not just that, it's choosing the right parameters as well within the algorithm. So building programs with these tunable parameters that then this program can adjust automatically over time and improve the behavior by adapting to the previously seen data, right? Your trained algorithm. Whoa, that was weird. So I drew this picture. Yeah, it's really basic, but I kind of like it because I mean, this is a basic introduction here anyway, right? So I'll just go through this really briefly, and for each section, I'll show you kind of where we're at in this cycle. But yeah, so it is a cycle, right? Like most even so data-driven as well as hypothesis-driven science, right, is usually a cycle. So, you know, for machine learning, it's super important, right, to ask a sharp question. Because if we ask anything vague, like, you know, you're a business, you have a small business and you want to know your travel, or not your travel expenses, but if you're basically, can I make more money next quarter is like a really bad question, right? But you know, for instance, what was my travel budget this quarter, and you know, what will it be for next quarter is a more specific question. So I have these little, you know, questions here. They're actually not the best questions. They're not very sharp. But you start with that, right? And then you go out and you collect some data. In this part of the workshop, we're using a very like pre-baked data set that comes with scikit-learn. So we don't have to collect anything. We just import it, which is really nice. In the afternoon, you'll see a little bit more complicated example of a data set. And then, you know, visualize and explore it, do some EDA, you know, look at your variables, maybe like a pair plot or something like that. And then, you know, obviously, like there's a lot of pre-processing, usually with real data sets, right? So clean your data, missing values, you know, dummying variables, like converting continuous to discrete when it is supposed to be discrete, you know. And then there's a lot of part of pre-processing is transforming your data, right? Like maybe you have like 1 million features and you're like, that's a really big feature space. Let's condense it down to maybe like the most important 1,000 or most important 100. And then, you know, and then at that point, we can choose an algorithm, train the algorithm, and get some sort of answer. And you see, I wrote answer and not solution because we really have to evaluate that answer. You know, we have to be thoughtful about that. And scikit-learn has tools for all, you know, this entire process, which is pretty nifty. And so, you know, if you want to do anything in the machine learning process, really scikit-learn provides that for you. I'm also going to use a lot of pandas for this as well. And they play very nicely together, which you guys probably know. So, moving on, let's just dive right in. Okay, so this is kind of abstracted from you, but I'm going to show you just this is still machine learning 101, a really simple case of a classification. And this code cell right here, the first one is our compatibility code cell. So just importing stuff to make sure it works with 3 and 2 or 2 and 3. So I'm going to put my cell you don't actually have to put your mouse in here, but I usually click in it and then shift enter, run it. Okay, so then the next cell is basically just to get plotting working. We're using matplotlib. You have to do something a little extra for Jupyter Notebook for plots to show up. So we go ahead and run that. All right, and as you can tell, like when you hit shift enter, it like advances to the next cell. So you can literally hit shift enter and over and over and over and run your entire notebook. All right, so I'm going. Yeah. I hit shift enter in this next code cell. I'm borrowing some code actually from Jake Vanderplas. I do cite him, I think up here, as well as putting his license in our repo because he asked us to do that. So, but as you can see, you have like some blue points and some red points, right? So what's the flat line? What's the straight line that's solid mean? Or what is that? Anyone, you can like raise your hand or speak up. Not quite. It's good. Separation, yes. So it's a decision boundary, right? Yeah, which is separation, totally. Yeah, it's a separation line, right? It's a boundary. So regression is machine learning too, and we'll get to see examples of that. So with this decision boundary, how'd that happen? Right? Like, what did I do here? Well, as you can see, so actually, there are two classes, right? There's the blue points and the red points, those are what? The word blue and the word red. Close, not quite class. Well, I'm looking for a specific word. So it's another word for the label or target, right? Well, it's not quite. Yeah, so it is classes. So definitely classes. So I was going for it's the label. It's your target. So label, target. Target's a really common word that they use in scikit-learn for your labels, right? So you'll see target over and over and over. It's the class name. It's the same thing. So I just wanted to let you guys know that, right? Like there's terminology in scikit-learn. It's most of you probably very familiar with it. So we have, okay, so what happened here? So let's look at our first scikit-learn classifier. So it's a stochastic gradient descent classifier. And we import it from some of the algorithms in scikit-learn. And here I'm actually I'm making my own data set. In scikit-learn, they provide you with a lot of ways to make fake data as well. So I'm using this make blobs, and then I let it know what the target names are. So it's blue and red, and then so let me run that. So I'm going to create my dummy data here. And then I'm going to run the next code cell with the stochastic gradient descent classifier. And you notice I have a lot of some parameters set in here. So if you really want to, you want to get help on a certain, this is true for actually any Python method or function, you put your cursor in right after the first open parentheses, and you hit Shift Tab. And the doc string comes up. It's pretty nifty. So then I can expand it and go down and see, oh, hey, what is the loss parameter? Like, what does it mean? What are the options? What are the defaults? So that's pretty cool. I use that a lot for scikit-learn. Just to, there's so many parameters with each classifier. All right, so when I want to train it, I use this word, this function fit. It's method fit. So I fit it on my X. Well, what's my X? That was the dummy data I made up here, this fake data. So it's two blobs. So I ran that, and it actually, if you just run it without setting it to a variable, it lets you know what all the parameters are that you use, which is quite nice. So let's go ahead and use the model down here. So what I would like you to do is, and so this terminology actually, not terminology, but these variable names are really common. Let me just go over that real quick. So capital X usually refers to our data, and Y, if there are labels or class labels, is our label, right? Also known as target. So that's all over scikit-learn and Python and other machine learning modules or libraries. And then when people split up the data into a training set and a test set, usually they'll just say X underscore train, X underscore test. So you'll see that over and over. So that's what I do in this code cell down here. I have X test. Well, I want you guys to go ahead and put a couple points in here. So, for example, these are XY coordinates. So if you put, it's going to be an array of arrays. So here's an example of some XY points, 0, 5. So you could copy and paste that into here. You could put more in as well. So go ahead and do that right now. You can go up to this plot and kind of guesstimate what points you might want to try out. All right. see, 9. All right, so after you have some data that you want to test, like a test set, right? So I have 3 points here. That's my test set. Then let's go ahead and try to create some predictions, some predicted labels for my test data. So go ahead and fill in this blank right here. So what would, well, you guys can shout it out. Like what goes into this little blank? So what we're trying to do is do a prediction. X test, yeah, exactly. So remember we did the fit method on X, and now we're going to put our test data set in here. So X test. All right, so I'm ready. I'm just going to run this code cell, shift enter, and I get some predictions. All right, so red, blue, red. So 9, 0. I'm going to go up to my little plot. 9's like way off the plot, but you can imagine 9, 0 is going to be somewhere around here. So it looks like it should be red, and it is. And then 0, 5, it's like here and here. Yeah, it's blue. It should be blue, and it was blue. So it looks like, I mean, I could check the third one, but I promise, it did a good job. So I have an accuracy of 100%, which is pretty nifty. All right, so let's go ahead and move on. I think I was, yeah, so it's 45. So machine learning can really only, and data science really can only answer 5 questions. These are not our sharp questions, but these are just the general questions you can answer with machine learning. How much, how many? So what's how much, how many? What kind of machine learning is that? Regression, right. Which category? Classification, awesome. And which group? Cluster, yep, that's right. Is it weird? Anomaly detection, yeah, and we're going to talk about outliers and anomaly detection in a bit. Which action? Close. She said recommender systems. Reinforcement learning. So like, yeah, your Roomba or your games or, reinforcement learning is which action. So it's kind of like also known as what do I do next? That sort of class of algorithms. So I have a link to a little Wikipedia article, which I thought was pretty nifty because it has, basically you can chunk like machine learning algorithms into either 3 different classes or 5 different classes. So, the first one is your supervised learning, you have labels and data, right? Unsupervised learning, you use it when you have data but no labels. And reinforcement learning, which I just, is it which action, is a reward penalty based information. It's also known as feedback. And that's the only one you really don't need to start with data, actually. So that's kind of cool. Reinforcement learning is not, there are no reinforcement learning algorithms in Scikit-learn. So that's kind of a bummer. But there are other modules out there like Reinforce that you guys can use for that. And then in that Wikipedia article, it talks about other ways to categorize machine learning, and that's in classification, regression, clustering, density estimation, and dimensionality reduction. So those actually are how Scikit-learn thinks about machine learning. So keep those in mind. Okay, so now I'm just going to talk a little bit about Scikit-learn, what you'll see. So if it's a supervised algorithm, you'll see some methods over and over and over. The first one you already saw, well, actually the first 2, a fit method, right, which takes your known data and your labels and trains your algorithm, your classifier, and a predicts method, which takes a new set of data and predicts the labels. So in unsupervised models, they have fit, obviously, that you give it your data, no labels, right? And then oftentimes they have a transform or a fit transform. So this is kind of fun. There's a lot of instances where you don't need machine learning. I'm a big fan of machine learning, but there's a lot of places where you just wouldn't use it. So I'm going to go ahead and skip over this, but I feel free to come back and ponder these questions at some point, because you know, there's examples such as pattern matching. Pattern matching, like regular expressions, is not machine learning, right? So, but it answers a lot of questions. Group by, well, that you usually, you know, that's like database stuff, and that's not machine learning. Data mining, not really machine learning, right? So there's a lot of questions you wouldn't use it for, but today we're going to talk about questions that you can. So we're almost done with this notebook. I just want to show you the diagram. This is probably, I think Andres Mueller drew it. It's an idea of what scikit-learn has to offer. So it's the algorithm cheat sheet. It's not an exhaustive list of what scikit-learn has, by the way. I just like the bubbles that it gives you, right? Like, yeah, it's kind of like, oh yeah, you know, kernel approximation, that's in my classification bubble. So it's kind of an example of what you will find in scikit-learn. And this is actually an interactive graph if you click to the original site, the interactive version. I have the link there. All right, so we're almost done with this notebook, but just before we wrap it up, our intro here, let's also do some more, just use some more classifiers that scikit-learn offers. Okay, so this set of data is the set we're going to use. It's called the iris data set. I'm going to go through it in the next notebook a little bit more in detail in the visualization and exploring part. But just so you know, it's a pre-baked, you know, readily like pluggable into scikit-learn data set. So it's ready to go for us. So I'm going to run this cell. Also, remember I mentioned that, you know, we split things. We split data sets. You guys probably know this already, but I call my training set x_train and the labels y_train. So here I'm actually taking my data set, the iris data set, and iris.data is where the data lives. Iris.target is where the labels live. So I'm leaving out one value from my data set. It's not usually what you do, but we're just going to do it here for illustration. Okay, and in the next cell, I'm going to use a logistic regression classifier. So what I want you to get from this is really like the process that you're going to use. And I've said a lot of this already, but I just want to solidify it. So you instantiate your classifier first. You don't give it any data, right? You just instantiate it, and then you give it the parameters that you want to give it at that point. Okay, and then when you fit the next line here, logistic.fit, that's when you train the model that you've already set up with all the proper parameters that you want, right? So, and then as you can see, there's a predict. This is a supervised learning problem. So our predict method that comes with all supervised learning algorithms, and I'm using it on this test set. And I'm going to go ahead and run the cell. All right, so I know it's kind of a small, goofy little example, but really the point was just to show you the flow that you'll see. So, all right, let's go ahead and you're welcome. There's some terms here that I just put down. A lot of you guys already probably speak this language, but these are our glossary terms that we're going to use throughout this workshop, right? So, okay, let's move on. Let's explore this data set. Let's see what it looks like. All right, so go to your second notebook, the R data set. I just put my pretty picture here again because I love it. So we're in the visualization section. We've already collected our data. It was super easy. We just imported it, right? And so you guys probably know this is an ancient and awesome data set. It's super tiny. It's Fisher's irises, right? Like, so what does a data set what does scikit-learn need a data set to be in order to function? And this is going to be true in the afternoon as well. Well, it's, first of all, it's got to have a certain shape, right? So it's like your number of samples, your number of observations by your number of features. And so that's true for your data set, right? And then there are your labels if they exist. So the labels or targets are just an array, which is the same length as your number of observations, if there are labels, right? If we're doing supervised learning. So also, just to note, the data needs to be a two-dimensional array, and it needs to be a NumPy array. So scikit-learn actually uses NumPy arrays and not pandas arrays because it's a lot lower level and it runs quite a bit faster. There's actually even faster options than NumPy because when you get into some seriously large data sets or deep learning, you'll probably need to use some very, very efficient storage options. But just so you know, yeah, scikit-learn, it functions all on NumPy data sets. Okay, here's a pretty picture. So, so what would be a sharp question? Okay, well, my sharp question is, what type of flower is this closest to of 3 given classes? So it's a very specific question, right? What does it say? Well, it says, well, I have 3 classes, and I'm asking, what does this belong to, right? Which group? So it's a classification issue, right? All right, so what are these classes? Well, they're actually the species names of 3 irises. And this is the iris data set. This is Fisher's iris data set, right? So we have 3 species, versicolor, virginica, and setosa. They're supposed to be a little different, right? Hence the classification, but they're all purple in this picture. So fortunately, we're not measuring color. All right, so I'm going to import some of these compatibility modules here. All right, so question for you guys. We already kind of talked about what you'd expect this data. What do you expect this is other than color, right? Like, what is this? What do you predict this data set is going to be? A lot of you are probably familiar with it, but what data, what numerical data would you expect an iris data set to have? Yeah, length, number of petals. Like width, yeah. Sorry, it's hard for me to hear anyone but in the front row. So if you're really passionate about your answer, please raise your hand and I'll like call on you. Okay, sorry about that. So yeah, so people said like they're numerical measures. So let's go ahead and see what the features are of this data set. So let's go ahead and load it. So datasets.load iris from the datasets submodule, scikit-learn. And this is just to emphasize, hey, yeah, they are NumPy arrays, right? So we have our data is a 2D NumPy array. Our target is a 1D NumPy array. Oh, and let's go ahead and import our plotting necessary modules and okay, so here we are. So all these pre-baked, these pre-built-in, I guess, built-in data sets all have the same sort of attributes. Sorry, I'm looking for that word. Attributes. So this data set, iris, has attribute feature names. So that that's our column names. Those are actually the numerical values that the classes of numerical values that are in our data set. So go ahead and run that. And you see, hey, there's 4 columns. There are four features to each of our observations, each of our flowers. So there's sepal length, sepal width, and petal length and petal width in centimeters. Okay. And you notice I actually converted it to a pandas data frame. Really, the sole purpose of that was so that it would print pretty. But we will use pandas in a more useful way later. So, okay, what about those targets and labels? So each observation has a label, right? And it's one of the 3 classes that you saw earlier: the versicolor, virginca, and setosa. So let's go ahead and look at those. And iris.target names is where you're going to find those. So if you use another data set in scikit-learn, it'll be dataset blah dot target names. Okay, yeah, we've already said this, right? There's 3. I just wanted to show you that you can get to those values, okay? And here's a pretty picture of what a sepal is and a petal is for an iris, just so you have an idea. All right, so this is really basic stuff, I know. We'll get to a couple of visualizations in a second. So let's just kind of click through these. So what's the shape? And really, what's the representation? What does it look like? How many rows do we have? How many observations do we have? How many features? All right, so 150 observations. Tiny data set, right? And then 4 columns, 4 features. And here's I want you to notice for this included built-in data set, you have iris.target or iris.data, and that's where all the data lives, right? Iris.target is where all of your labels live. It might be useful in the future when you have your own data sets that you're importing to keep that consistent. That's just a recommendation because it will, it'll make a lot more sense for you and other people that come and use your algorithms, your, data, etc. So, all right, so here I'm using pandas for a little bit more of a useful thing. I'm putting the data into a pandas data frame and giving it labels so we can see what our columns actually mean and taking a look at it. And this is how I would normally do some sort of exploratory data stuff. So I want to just see the first few. And here are the values that you're going to come across for like sepal length and width, petal width. Okay. And pandas has a lot of handy functions like describe. And describe is the way you can get your summary stats, right? So your like quantiles, median, mean, etc. So you see your maxes, your mins, etc. Just give you an idea of the numbers and that you're going to see in the plots, right? Okay, so let's look at the data real quick. So I just like to import matplotlib again just to make sure. We've already done that at the top, but let's go ahead and do that again. We convert it to our data frame. And that's because matplotlib works a lot better with that sort of format. So go ahead and run this guy. Whoops. Oh, fun. See. Yes. All right, well, here's a homework assignment for you guys. Right? I apologize that this box plot isn't working. So, but a box plot is available in Matplotlib, and I highly recommend using it. And you do tend to use this pandas function pivot that actually makes the data. Pivot will take data that's in long format and convert it to wide, right? And that's very useful if you're going to do a box plot. So, or even converting. And pandas also has a melt function that goes in the reverse, wide to long, just so you guys know, okay? Hopefully this one works. So here we're going to try a pair plot with our iris data set. And this one's pretty neat because you can see separation in this, and you can also see correlated values. I think it's pretty neat that you can see these guys are highly correlated, right? So, wait, is that? Yeah, and then some of them actually separate out the data, right? So that's a really handy plot. All right, so that wraps up our real quick whirlwind data exploration and visualization. There's obviously a lot more you can do with Matplotlib and Pandas here, so keep exploring. I put some pre-processing options in here. I'm not really going to go through it, but it's good to know that you can normalize and standardize your data sets in scikit-learn as well. And you can also do some regularization. So, are you guys all working on the plot problem? If you guys fix that, you're welcome to post it to the Slack group. Thank you. Oh, and also I'm not sure if you have Seaborn installed. So Seaborn is another plotting module built on top of Matplotlib. So if you want to import anything or you want to install anything like on the fly in a notebook, you do !pip install module. Exclamation point is actually a I'm not sure it's a magic. It's a Jupyter Notebook specific syntax for do a OS system type command. So I can actually run another Python script that's on the command line with this sort of syntax. So it's just a way to interact with the OS. So fun note. When so Jupyter used to be IPython, right? And it was only a Python kernel. That was it. That was all that was available. This is like when it was first born, probably like 15 years ago. Fernando Perez actually designed it to be just an enhanced version of the Python interpreter. That's it. That's all it was at the beginning. No browser stuff, none of that. That happened much later with the advent of some technology that allowed it to communicate with browsers. And other funny note, as I open up feature engineering, which is the third notebook here, is that Windows users back in the day, they didn't really have like ways to explore their OS. So a lot of Windows operators, people with Windows adopted IPython to interact with the OS. It was just kind of a random funny thing. So now it's Jupyter. It's come a long way. And Jupyter, you guys probably know this, but refers to the fact that it's Julia, Python, and R are, fabulous data science languages. And Jupyter actually supports over 50 other kernels, so 50 other languages. They're not all created equal and not all easy to install, but just so you know, they're there. It's pretty awesome. Yes? So a pip install. Yeah, that's a good question. So I'm running it right locally. I'm running a not conda install. So I use pip, but you can actually, that's a really good point. I apologize. Yeah. Those who are using conda, would type, instead of the pip, exclamation point pip install blah, you do exclamation point conda install blah. So thank you. Yeah. Oh, yeah, it's actually, that's a good question. I'm not sure. I think it's installing on the machine permanently. Thank you. Okay, yeah, great. Yes, thank you for that. That's true. Whatever environment you use to start the Jupyter Notebook is the environment where that install will go. Oh, whoops. I did open the next. Okay. So let's move on. Feature engineering. Yeah, that sounds like really boring, but it's actually super important, right? It's very important parts of the pre-processing path that we're going on, right? So I said clean data because in parentheses, we don't have to do that with this data set. That's going to be super important in the future, though, for your data sets. Really good to take a look at what's going on in your data sets, especially that like description of summary statistics type of stuff, to see if you have any really weird values like NAs, maybe numerical values that are really supposed to be categorical variables. So it's always good to take a look at that, and then clean up anything you need to clean up. So Pandas is where you're going to probably do most of that data cleaning. All right, so we're just going to go through a little bit of feature reduction, selection, and creation with scikit-learn on our iris data set. So I love these methods. They really make life a lot easier, especially once you get into those really huge data sets. So I'm going to start. This is just a little pretty picture. That's a petal, that's a sepal. Okay. Let's go ahead and import our compatibility modules here. And some plotting stuff, plus NumPy and Pandas. All right, so we're going to start out with it's actually a Python a scikit machine learning algorithm called select k-best. And I just realized we've been going for quite a while. So let's pause here and take a 5 or 10 minute break. So you are welcome to get up and use the restroom and grab some coffee or water. By the way, if you don't know the restrooms, you go like straight that way, past the coffee, etc., towards the doors you entered in. You take a left and go down that hallway, and there's a sign for restrooms that you can follow. Or 5 to 5. These other ones will start.
I actually figured out what's wrong. I don't know how to fix it.
Okay.
So the problem is that we're doing the list of range star 3, and when we do that, it's expecting all of the indexes to be unique. It's not. So I tried making this 150 and getting rid of the 3, but then I ran into a different error. So I'm not quite familiar with how any of this works. I figured if you put it into a set or something, or like.
So I was trying to get it to use the index is like 0 through 50, 0 through 50, 0 through 50.
Yeah.
Or not, 0 through 49, 0 through 49, 0 through 49. To give those like ability to pivot or like classify those guys.
Right.
Yeah.
Yeah, classify those guys.
Right.
So we tried like just removing duplicates, but
oh, no, we just try removing duplicates, but obviously it needs 150 values, and it's expecting that many.
yeah. So now when I can replace the duplicates with like dummy values, or actually if you scroll up, that's where the table is populated. Oh.
So there should be 150 values total is what I see. Can we just create it randomly? Like, can we create 150 random values? Or does it have to be?
Wait, no. No, then the graph won't be.
Yeah, the graph. I mean, we can still create random values between 0 to 50.
Sure.
But
No, you could, yeah. I just went into like, you know what I mean? Like in a consistent way.
oh, I see.
Times.
Right.
Yeah. Let's see if I fix this. It was weird because it was working. I feel like I'm missing.
Seems like there's some. Yeah. But feels like something else is wrong at this point. Saying. Yeah. Oh, so what I had to do for that was just compile everything from the beginning so that it knew what DF was. But... yeah, like I had to do all of the different, yeah.
Because I just ran it.
You probably also then need to do like import something as DF.
Yeah. Oh, yes. Yeah.
Yeah. I just got df equal to this stuff.
Yeah, that's very
Oh.
Oh, it's the D. It's so weird. It's because I have these two names. What's DF?
Oh, there's.
This should be Iris. Yeah.
Okay.
It's one change. Thank you so much.
Yeah.
You guys are like inspiration.
All right. Glad to help.
I'm gonna fix it and check it back in.
Okay. That's good. Thank you.
Yeah.
I just hit it. Well, I tried the binder and it didn't.
The way you usually how do I do that? It's like Jupyter Space.
Oh, right. I have it. Yeah.
And then you can type Jupyter Space. I was trying to see my dad.
So I know almost nothing what you're doing. I know something with Python, but nobody knows absolutely, yeah, absolutely. No, I work with Python every day, so I can fix it. But I don't. I have a friend I have a friend that's in corporate college who works a lot with this and goes on and on with virtues. I'm like, it's great, but I don't. I'm a security. I do Python, Java, C++. Python is actually my general purpose. Like, I write a lot of scripts for like systems purposes, like I'm security. I have to write a lot of scripts for like general. I need to know what's happening on 100 computers. That's quite done. So yeah, this is great.
Yeah.
I'm just gonna go to this. Or I'm just gonna try to run this. But if I want to do this, so
So no. Yeah.
You know, it's very strange. I downloaded it and I rerun it. It's the same thing. You downloaded it again. Yeah. Yeah. Did you have it? It's not every. I did a. Oh. You can download it. Yeah.
Hey, got an issue with this error.
Yeah, me too. And it's not this.
Yeah, I was about to show you guys.
Oh, you did? Okay.
Typo for me.
Okay. All right.
Yeah, I also, as I go back to the GitHub page, like the repo on GitHub, I fixed it. I just checked it back in.
You don't have
Here? Oh, no.
Your repository, like go to GitHub.com.
Oh, okay.
Oh, yeah. So that's much easier. Yeah, I mean, again,
There is that, you know, like there's target and but how do we have to find that?
it's not even machine learning. It's more distribution. Yeah, it's like
so if it's like say high medium low, then that
so
would be
when you close
so it'll automatically know that you don't have to.
So when you do any changes to this,
And then so if there were other names, then yeah, I'm getting that error on
so you can put it in so what I
yeah, like so in the next block for you.
Right.
Okay, so this
I did. I mean, I kind of like.
All right, guys, let's go ahead and plow forward. So if you guys could take your seats, hopefully you had a nice break, had some coffee or water, aren't too wired, like perfect level of coffee. So one thing, that error on that plot from, I believe it was it? Two. Thank you. Two. Yeah. For some reason, I have two feature engineerings open. Okay. So, in two, if you recheck out or go to GitHub, the Python workshop GitHub intro to sklearn, I fixed the code and checked it back in. So the solution should be up there. But I just wanted to show you guys as well what the plot looks like super fast before we go to feature engineering. This better work. Okay, so it was a typo on my part. Between, I had some silly naming here going on, my iris.df versus just df. So I apologize. I kind of made that right. And so the plot looks like this. It's just one feature. So it's a super simple plot. I just wanted to show you guys an example of what I would do if I was exploring the data, right? So this is just a sepal length plot across the three classes. So. Okay, so selecting top features of data sets. So this is a dimensionality reduction, right? I'm gonna move this up a little bit so I'm not crouching. All right, so make sure I'm just gonna go ahead and re-import this cell, do some imports again to make sure the plotting works. So it's the matplotlib inline code cell, shift enter. Okay. So select k-best. I'd say this is the really the simplest you can get as far as feature reduction, feature selection in scikit-learn. Basically, it's just gonna use a p-values or another calculated statistic to let you know which feature contributes the most significant, in a way, the most significant separation for your data. So I import everything. So it's in the feature selection submodule. It's called select k-best. I also import chi-squared statistic, or actually it's a method, because we're going to use that in select k-best as our score. So I'm going to shift enter. As you can see, it's our original 150 by 4 data, right? Remember, X is our data, Y are our labels. So in this cell, just for fun, and actually just to show you things you can do with your data, I add another feature. I add another column. And I was curious, about ratios, right? So I looked at, I guess I'm looking at the ratio here of petal width to sepal width. So I'm curious, right? Like the petals, they looked pretty skinny, and the sepals looked really wide. So I was like, well, I wonder what that's like across the 3 different classes. Anyway, so that was my logic. You could create any extra columns you want, right? So I'm creating an extra column, and then I'm going to reduce the data set. So I do this with pandas. So I convert my data to a pandas data frame. I give it some column names from that, pre-built-in attribute dot feature names. Create my new column, my new feature, and then I want a new feature names to represent all those new, to include that new one. Then I'm going to print it and then reassign it to X. Okay, so shift enter, run that. Here I'm just printing my array of the column names, the feature names that now correlate to X. All right, so let's go ahead and run the feature selection, feature reduction. So here I I tell it to use chi-squared as my scoring function. So remember, I had to import that. And just like in all the other scikit-learn algorithms, I set it up with my parameters first before I give it any data. Okay, so that's what I'm doing here in this line. Dim red is dimensionality reduction, kind of a silly name for a variable, but or not really. So then we do our fit, right, with our data and our labels, and transform. So that's a new one. Remember I mentioned if you're in the unsupervised category of scikit-learn algorithms, you'll find sometimes a transform method or a fit transform method, which actually does the fit and the transform all in one. So yeah, it's actually considered an unsupervised algorithm. But I like to think of it in the transformation pre-processing step, right? So I'm gonna run that. All right, so now I have a transform data set. Oh yeah, up here when I set up my algorithm, I said k equals 3. That means I want 3 features of my 5. So I want the 3 most important features or significant features. So the select k-best and other of the univariate type dimensionality reduction algorithms, you can get to the actual scores that are assigned to each of those original features that you fed into your classifier. So as you can see, remember we have like 5 columns now, right? It's like, I forget the names of them, but you can scroll up here. There's a score of 10 assigned to sepal length, you know, et cetera, et cetera. You can see there's a 23 assigned to our new column, new feature, pedal width over sepal width. All right. And then our new shape of our transformed data obviously has 3 features, right? That makes sense. So what columns were selected? So I get back to that using the get support method, which actually gives you some Boolean values, and then I can kind of map that back to my feature names. And my feature names, remember I put it in that new feature names variable. So I just map that back, and here I get the top 3 for my iris data set. And hey, you know, my new features included. So apparently that was a good call, right? So just so you know, the scoring functions in select k-best, you have a few options. If you're doing classification like we just did, there's chi-squared and an F classifier. And then if you're doing regression, you can also do that type of algorithm with your data and do a select k-best using that that process. You use F regression. I think that's the only option. So there are links out to those pages on the scikit-learn documentation. Okay, so PCA, like that's one of my favorites. I remember learning about PCA a long time ago. And I never even like linked it to, I mean, I learned about it like 12 years ago. I never linked it to machine learning, but yes, it's a machine learning algorithm, right? It's super useful. So PCA is more complicated than select k-best. So why is PCA more complicated than select k-best? Anyone? Please. What's... Yeah. So yeah, it's true. There's in PCA, and we're not really going to talk about that, but you have eigenvalues and eigenvectors. So those correspond to something called components. And the thing about PCA is you really don't get, this information like we got with top K or select K best. We won't be able to get back to the actual feature names because the PCA algorithm doesn't give you that information. It's a little bit more complicated. So I'll show you what I mean. So it's in the decomposition, which makes sense, submodule. And so here we go. let's go ahead and run. Well, let me tell you about this code cell real quick. So we do our classic data import. Then I set up my classifier, right, or my algorithm here without the data yet. So if you want to see what parameters you can give to PCA, you can put your cursor right after that open parentheses of the algorithm name, PCA, and hit Shift Tab. Well, at least in theory. Probably have to run it because I have to import it. Usually, yeah, sometimes it's like that way. Okay. Yeah, I had to import it in order to see the doc string. So anyway, I just wanted to show you guys that. It's let's see. Here, this is actually the end components. Excuse me. I was really sick. I was like actually traveling for 20 days. I got back yesterday, and you know when you travel and you have all this stress and you have all this stuff going on, and then it like ends and the stress ends and you get sick. Yeah, that's what's going on. So all right, so you can either put a number here for end components, like an integer number, or a percentage in a 0 to 1 format. And I'm trying to get to that. To basically, okay, so the percentage, yeah, I just wanted to be clear about this. If you put a float here, it actually knows to do something different than an integer value. Basically, it'll correlate to my desired amount of variance that is needed to explain the separation in my data. Okay, just wanted to be clear about it. And I kind of wanted to show you that option because some people don't know you can do that with the PCA method. Okay, so then it's unsupervised, right? So when I do a fit, I only need to give it my data, right? So it also has a transform method, like a lot of the unsupervised algorithms you're going to see in scikit-learn. So here, I guess I'm just looking at the first column for some reason. So am I trying to print this? Probably. Apologize if that's not there. I think I'm trying to print this. I have a lot going on in this cell, so let's not worry about it too much, because I actually say here, please don't worry about the details of this plotting. You can go through it later, and I can explain it at some other time if you want to come up like after this and go through it. You're welcome to do that. But go ahead and run this. Oh, I see. I don't want to print that. Oh, a shortcut that I love to comment out a line or a whole swath of lines in a Jupyter Notebook is, so if you're on a Mac, it's Command and the /, like Command plus /. Or if you're on a Windows machine, it's Control /. So I love these little shortcuts. All right, so Command. And then to uncomment it, it's the same. So, okay. Yeah, so I printed out all my data there. So this is what I actually get from PCA. If I only look at the first principal component and the second principal component. These components do not correspond back to the feature columns. It's actually combining everything together and giving us like attributes and information from all of our data in a reduced dimension. So you can read more about it, on Wikipedia. And I actually have the link right here. Read more about it on Wikipedia here. So, all right, so you can see there's some separation going on. This is our first, I believe our first real visual of this data set. So here are 3 species. So it looks like Virginica and versicolor are a lot more similar than Setosa. It'd be fun to look at those pictures again, but we're not going to do that. All right, so moving on. This is a bit different. One-hot encoding. So have you guys heard of that? What is it? Anyone? Yes.
Basically, you create the label into a binary so that there are 10 of them, you create a vector, and the fourth one, the fourth is one, the rest are.
Yeah, exactly. So Cyril? Yes. Yeah. That's exactly right. So basically you have like, your labels and in one column, right? So imagine with our iris data set, they're actually numerical integers, like I believe, can't remember which one's which, but we looked at it in our exploration of the data, but you have like 0, 1, and 2 in our target, in our labels for this data set. So one-hot encoding will actually think about like transforming that column into 3 columns, where the new names of the columns are actually the labels. If that makes sense. Hopefully that makes sense. And then in each column, instead of being like 0, 1, or 2, it's going to have like a binary value that associates that particular observation with a label. So let me show you. All right, so we use our wonderful pandas trick here to deal with it. Because pandas actually, so scikit-learn has an option too, but pandas has a really nifty, quicker option, I believe. Well, not quicker, it's probably slower, but easier, more abstracted, easier to use. So maybe don't use the get dummies if you have a super big data set. But here it's super small. So load my data and then, convert it to the data frame, pandas data frame. And I also, when I do that, I need to add, so the columns are actually the features, right? So I have to add my target values. And here I'm actually encoding them as actual strings. Because remember, the target values in the data set, and actually target values in scikit-learn data, they have to be numerical. So that's why it gives you all these data sets as like dot feature names, dot target names. That's to get back to the string values. Okay. So I want them to be string values, so I encode them here into a new column in my data called target name. And then I use the pandas get dummies method, feed it the data, and let it know which column I want it to dummy or one-hot encode. Okay, so I should have added the original column here. I think I transformed it out. But here are features, right? And remember, I had one column with those values, those integer values, 0, 1, 2. Well, instead, I now have 3 columns, where the first one is our Setosa, or 0, label, and a binary. These are supposed to be integers, but yeah, binary values that indicate, well, is this row or observation correlated to a Setosa iris, right? Okay, so if you look at also the tail or last values of this data frame, you see there's binary values for the last one, for the Virginicas. So you can look at the whole thing if you want as well. It's only 150, values, but. So that's dummying in pandas. And then here's the scikit-learn method. It's about the same, except you use 2 different methods, 2 different algorithms, so to speak, one-hot encoder and label encoder. That's just because of the fact that labels in scikit-learn are numerical. So it's getting back to the string values again. And it's a little less slick than the pandas one. You'd have to recombine this data frame with your original data frame. So. Right, cool stuff, huh? All right, let's do something more exciting. Yes, sorry.
Maybe I missed this. What is the advantage of converting your classes, your outputs to dummy learning?
Oh, I apologize. Yeah, that's an excellent question. So oftentimes we increase our feature space by one hot encoding or dummying variables. Yeah, this is thank you so much. That's a really good point. And so think of that as then you actually have more features when you dummy, right? When you one hot encode something, you get more columns. Well, those are actually, that increases your amount of data, literally increases your amount of information. So say, for instance, instead of our label, actually, yeah, no, it adds, that's actual data it adds. Anyway, so those could be possibly potentially important features in your data, right? Just indicating whether or not it's a Setosa iris, right? Instead of, well, what class is it? Like indicating, is this Setosa or not? That could actually be a question you have of your data before you start exploring it. So then a lot of people, so you do get a lot of features, your feature space, you could really go to town with this, right? And then you'll do usually a feature reduction or dimensionality reduction to get back to what is the most information-rich part of your data. So thank you. I actually find that part the most fun, but I'm really weird. So let's look at some learning, some machine learning. So I'm going to notebook number 4. All right, so I'm just reminding you, like for the 100th time apparently, that these algorithms in scikit-learn have a fit and a predict. Okay, so yeah, let's hypothesize about what we'll do. This is a super small labeled data set, right? So what algorithm would you guys choose to do some predictions when you come across a new flower on your hike, up a mountain? I was about to say Mount Rainier because I'm from Seattle, but you see a pretty flower, like, well, what algorithm would you use to create your predictor learner to do a good job at picking the right class of flower? And by flower, I mean you run into an iris that can only be of 3 different classes. Yeah, so that's a great algorithm example. Nearest neighbor, k-nearest neighbor. I mean, it's, yeah, so we could use that for sure. Yeah, so other supervised algorithms. Logistic regression, right? So that's very, very, very applicable to this data set. So that's a really good idea. Yeah, so it's good to definitely think about what would be the best approach, right? What would be the best algorithm for your question? Yeah, and so this is from the docs, actually the scikit-learn docs. I think it's great. Often the hardest part of solving a machine learning problem can be finding the right estimator for the job. And actually, it's been oftentimes recommended, try 2 or 3 on your data set if you have the computational power, right? It's highly recommended to do that. And then parameters, are another dimension. So we'll talk about that a little bit later. Okay, so I just looked at the time, and then one of my volunteer friends over here. So we have 10 minutes left. So I'm just gonna. David's not here. Oh, the food's not here. We're gonna keep going until the food gets here. How about that? Then you'll be like really hungry. Like, ah. Okay, so we may not get to the stuff later after the learning part, which I think is also just super duper important. The evaluation methods. So getting your accuracy scores, looking at confusion matrices, stuff like that. You can do in scikit-learn. So highly recommend to go through those later notebooks. And then I think at the end, I show you how to do parameter tuning with grid searches. That is also super, super slick, really nice way, especially if you had a really big feature space, or you just have a lot of questions about, the parameters. You're not sure, maybe you're unsure about the algorithm like itself, and you want to try a whole bunch of different parameters for a particular algorithm. Grid search, I think it's called Grid Search CV in scikit-learn, is a fantastic way to optimize your parameters. Okay, let's do a little bit of supervised learning, and then maybe we'll get to do some unsupervised. Okay, so in this one, I wanted to show you this whole submodule of scikit-learn. Not the whole thing, just an example from it. And it's just a tool called train test split. It's really nice because it does exactly that, right? It splits my data into a training set and a test set in a very stochastic way, or a very random way. And I can tell it what percentage I want my split to be. So here I say, please put 70% of my data, of my observations, into a training set and 30% into my test set, right? So I use these, you're getting familiar with the naming here: X train, X test, Y train, Y test, where, Y's are our labels and X's is our data, right? So let's go ahead and run that. All right, so we have now split our data into these variables. And you have to put all four variables here. This is actually called in Python, you probably know this, but variable unpacking. Okay, so I'm actually going to try a decision tree. I encourage you to go ahead and try other algorithms like the logistic regression and k-means. No, I'm sorry, it's a k-nearest neighbor. But here, just going to show you decision tree because I have a fun graphic to show you after. So I put some parameters here. Actually, if you want to learn more about them, do the shift tab trick and get the doc string. You could, of course, just go to the scikit-learn documentation website or Google it. So I define my classifier, right, with all the parameters. Then I do my fit to train that classifier. And then I get to the score by giving it my test data and my test labels. So does anyone know it's kind of a guess, but what this performance metric is, what score is in scikit-learn? Yeah, it's the accuracy. Awesome. Yeah, so you can get to other measures like the precision, the recall, the F1 score. I'll show you guys that, but it's in the notebook. I think it's in the evaluation notebook. Okay, so you can get to those scores as well. But when it says score in scikit-learn, it usually means accuracy. Right, so it's a 95.5555% accurate model in this run, right? In this split. So check. Let's go ahead and check what label it is. What's that? Anyone? Oh. So fill in this blank right here. So basically, okay, so what's going on? I'm getting a prediction of labels. So I'm getting a set of predictions from our test set, right? So it's actually 30%, remember, of our data that we're testing on. And I print those predictions. So it's going to be like an array of numbers, 0, 1, or 2. And then I print it down here. And what I want is my prediction, right? Which I'm actually just looking at the first one, okay? So it's Y prediction, the first value in the array. And then I compare it to my original label. So go ahead and fill that in. Its original label is Y. No, wait, was it Y train? Train. Tests, yeah, sorry. Right, Y test, because that corresponds to that 30%. Okay, thank you. Okay, so you can see, remember those integer values that correspond to the iris class. And then I'm just looking at one, of my predictions, and hey, look, it did a good job. So, of course, there's way better ways to look at the whole data set. And then, okay, so I want to show you guys, actually, we're going to skip over this, but just so you know, in cross-validation, submodule, there is a cross-validation cross-val score, and with this really nifty method, because it actually does the split, and it does the training on a classifier, the testing, and then the scoring and evaluation all in one. So that's a fun little abstraction. Scikit-learn has a lot of these abstractions. So they're actually really handy though. Okay, so down here, I actually installed some a module on my local machine, and I had to install a couple other things. So this may or may not work for you, but I encourage you to go to this guide if you want to look at this graphic. But I'll just show you guys real quick. It's just a really nice way to see the decision splits for this tree. So if you're unfamiliar with decision trees, this is like a really nice way to visualize what's going on in this particular data set, in this particular classifier. So I think it's pretty nifty. So if you scroll down, see like you have your setosa. The split is on petal width, and it's really easy to get to your setosa that way. So you're like, oh, maybe petal width is a really important feature that separates out the setosa iris from the other two. So it's kind of what you can see here. All right, so did I score this? Actually, you want to go back up here and run this code cell. I'm sorry, just pop back up above the GraphViz stuff that I just did, and run the cell that has that cross-val score in it that I just spoke about. So I run it, and I get 3. Also, it runs the validation like 3 times, which is kind of neat. So, which is what validation is, right? But it does 3 tries, or three sets, 3 splits really. So I have all these. So I have 3 scores, 3 accuracy scores. So what do you guys think? Are these like too high, too low? What does 1 mean? What does that indicate to you? Yeah, it's 100% accuracy. Too high, right? Overfitting, yes. So look at your accuracy scores, because I know that there are a lot of other metrics too that you can look at, but in this case, it is actually overfitting. So it's kind of a red flag when you sometimes see 100% accuracy, along with some other ones that are rather different. So just something to think about. It really is relevant, like for big data sets. This is a super tiny one, but just so you know, look out for that. So what can you do with if you have a decision tree and it's getting overfitted? What's the next algorithm? Yes. Oh yeah. So okay. So the cross-val score. That's a good question. Okay. So it's doing cross-validation. So in that case, what is actually happening is it splitting your data 3 different ways. So it's running the split 3 times, and then running the classifier training 3 times, and then you get 3 accuracy scores from that.
So basically, it's dividing up the data set 3 ways.
Exactly. It's dividing the data set up 3 different ways.
Okay, okay, sorry to be arguing.
No, not at all.
From my perspective, I don't really see a huge problem in this case because even though the last one has 100% accuracy, the first are like reasonable. So
Yeah, no, that's a great point, right? So in this small data set, it's actually doesn't really indicate much. But once you get into really big data sets, it's really not, a hard, fast rule. Like if you get 100% accuracy, like, oh, it's a terrible algorithm, don't use it. It's just something you might want to investigate. So that's all I was really saying. So yeah, that's a great point. It doesn't necessarily indicate it's a horrible model, but it, in this case, actually is, and so it does occur sometimes when you get, those scores. So.
sorry to follow, this accuracy relates to the training set, right? Not the test set.
Oh yeah, so that's another good point. This is a really abstract method. So it is splitting into training and test. And so the accuracy score is on whatever it's split into test. So it's an accuracy score of the test. Yeah, good question. All right, so oftentimes, and I'm gonna actually skip over this. Our food is still not here yet. Oh. Great, yeah. So what do we do if there is overfitting? Because a decision tree is just, it's just one way of splitting, right? So there's another algorithm out there that oftentimes people use. Well, there's a couple different ways, but oftentimes people will use a decision forest algorithm when you encounter overfitting in a decision tree. Okay. You can also do a boosted decision trees too. Those exist, and I'm not sure what it's called in Scikit-learn, but here I'm gonna, what's it called? Add a boost. Okay, cool. Yeah, thank you. Awesome. All right, so here I'm gonna do my old train test split. So let's go ahead and give this random forest. Actually, was I gonna? Yeah. I'm gonna let you guys go ahead and do this on your own. Okay. Go through this notebook, the rest of this notebook. I just want to show you a little bit of unsupervised, some of the unsupervised methods that you can use in Scikit-learn. And we're almost done anyway, so. I'll just run it. Okay, I just decided to not do that and run it. So you can see, the not abstract, the not cross-value score, just the test train split. You get a 97.777% accuracy. Then we try our cross-value score method, which does all that wonderful abstract stuff for us. And these are our scores. So, okay. All right, let's look at the 5th notebook. And we may have time. Well, we'll just see how much time we have. Okay, so apparently we have about 10 minutes. So after unsupervised learning, I have that model evaluation that I told you guys about. So, please check that one out. That goes over like the confusion matrices, ways to get your precision, recall, F1 score along with your accuracy, okay? And then pipelines and parameter tuning. Parameter tuning is where you can get more information about that grid search CV, where you can actually like tune the parameters of a classifier before even doing like fits with it. Or no, you grid search with the data, I believe. But anyway, it's a really nice way. It is a little more computationally intensive, but a nice way to tune your parameters. And then pipelines are even crazier and more abstract. You can actually literally pipeline all that we've been doing, all the like transforms, pre-processing, actually like training your classifier, testing your classifier, evaluating your classifier, like all into one line of code. So just so you know that exists. Actually, that pipelines are relevant to the afternoon stuff, to the TensorFlow stuff. Oftentimes, the TensorFlow stuff is put into a pipeline. So that's kind of a good thing if you guys want to take a look at that. Yeah.
The result from the previous test is not random.
Cross-file score? Let me get back to you on that. So someone was wondering if the cross-file score, that splitting of the data, that 3 ways, different ways, is random. And I am not sure.
Because I run it 5 times. So we don't set the seed, so it's random. You see the seed.
Right, it is random. Yeah, there's no seed. Yeah. Right. Yeah, that's actually a good point. In some of these, oops, I'm in unsupervised, but in the supervised learning module, there's a parameter in the classifier that I put called random state. I did that because it actually gives me the same, it gives me the same result from, wait, let me take a look. Actually, yeah, I'll talk to you guys about that like after, but all right, so my hand-drawn thing again. So here's a little bit more PCA. So I import my compatibility module, my plotting stuff, and you know, this is a little bit more in depth of PCA. Excuse me. But remember when we were talking about PCA, we had those, like we actually plotted the components like 1 and 2 on a graph, and we saw the separation of our classes of viruses. Sorry, I'm like, I feel like I just need to like hack up a lung or something. So in the PCA, there's all these like standard attributes you can get to of like transformers and classifiers. So for a lot of the dimensionality reduction and the transformers, well, this is specific for PCA actually, but you can get back to the % of explained variance associated with the component, as well as the information on the component itself. So that's the direction of the spread that it can explain. So it's like the explained variance is the magnitude of the variance explained, and then the component's attribute of PCA here represents the direction of the spread. Okay. So I'm going to run this cell. And what I get here is just the fact that I'm choosing in my data set column 2 and 3. I kind of just decided that at random because I wanted a 2-dimensional data set. You can, of course, change that. And then I set my components equal to 2, which actually means, I'm only going, I have actually 2 columns and I want 2 components. But it is combining all my data into the most significant values that explain the variance. So then this variance, you can see I converted it to percentage. So 95% of the variance is explained in that first component. It's like, really, we may only need 1 component, but we're using 2. You see, it's just that other one doesn't explain a whole lot. And then the components for each feature, they're XY values. Okay, so let's take a look at the plot. Don't worry too much about what I'm doing here. Basically, this is just for plotting purposes. I'm trying to plot like the vectors and also, their magnitude on a PCA plot that is like component 1, component 2. And so you can see the spread of that data and the component's contribution to it. Yes.
Can we get an idea of what the components are? Or it's not our original.
Oh, the numbers, like the eigenvalues, or no?
What are the components that contribute to nice? What features contribute to the components?
Okay, that's a super good point. What features contribute to the components? So PCA is a little, it's more complicated than say the select K best, which you can actually map back to feature names. In PCA, you cannot map back to feature names. Yeah. It like transforms your data, yeah, into new columns, but those new columns don't. Yeah. Exactly. Right. It's transformation. Yeah, PCA is a little bit more complicated, right? Than the select K best, and it's a transformation. It gives you back like numbers that aren't actually your original column values. All right, so in this plot, what's going on? So I have a X value, X axis, which is my so I'm just plotting my original data. I'm plotting the two features that I selected. Remember up above, it was like column 2 and 3. So this is column 2 was sepal width, column 3 is petal length. So these are the original data points. If you plot just those two columns and as a scatter plot, and then the black lines are basically the explained variance, which is like our magnitude of how much a component contributes to classifying your data or giving you information about classes, spreading out your data essentially. And then the direction of those vectors is the information you get from the components part. And it's kind of neat because it shows you, hey, like this is the direction. So this little guy, right, the smaller guy, that's the direction of the smaller contribution. And then the bigger vector, which is more vertical, is saying, hey, look, a lot more variance is explained in this direction. And you can kind of see that, right? Because that longer line kind of corresponds, if you look at, imagine drawing like a line completely through the plot, the separation of two different classes. And so you can see that in that direction. I think that's kind of cool. But yeah, PCA is a little harder to visualize. It's a lot harder to visualize than just, the selecting K-best, especially when you start doing PCA on really large data with tons of features and your dimensionality reduction is like to 100 components, then it's just 100 dimensional space, right? So, all right, so this is a little bit more about PCA. I'm gonna let you guys do this exercise. Basically, we're doing PCA again, and we're keeping 95% of the variance, but we're doing it with our 4 features, right? All 4 features, instead of me saying, I want column 2 and 3, or 1 and 2, whichever ones I picked. So, all right, clustering. That is like a hugely important algorithm. Well, I mean, they're all very useful. Clustering is just so common these days, right? Like what group? It's used a lot. I think it's used a lot in like recommender systems. Like what group does this customer fall into? I don't necessarily label those customers, I just group them. I want to know what group they're in. And then maybe I associate like certain products with that group. So here I'm going to cluster my irises, but I don't really care what the labels are. I just want to see the structure in the data, right? Clustering gets you back to the structure of the data. What does it really look like when you run an algorithm on it? Groups, I guess, is what I'm trying to say. So I'm installing this IP widgets. IP widgets is actually just a way to create some interactive graphics in a Jupyter Notebook, which is pretty nifty. This was not working for me yesterday, so it may not work for you guys. In fact, I mean, it'll run, but the interactive part wasn't working for me. But I'm going to give it a try again. Also, I believe should I mention... Okay, it gave me a really long message saying that I have this module already. So if this doesn't run for you, don't worry too much about it. I think on the static version on the GitHub repo, it shows the results. Okay, so here we're doing PCA, just like we did above. This time I'm using fit transform, which combines the fit and the transformation into one line. So as you can see, I said, oh, you know, for my 4 features, I just want 2 components that explains the most variance. Okay, so k-means, what is that? Well, let's look at it in a picture. Maybe this interactive thing will work. So I actually, in k-means, I'm not a big fan of k-means, actually, because you have to tell it how many clusters a priori. There are a lot of other clustering methods, and you'll find that in scikit-learn. I just find that to be not ideal for some data set that I've not seen before, right? So if it's some data you have an inkling of how many classes you're going to get, then k-means is for you, right? So. Okay, don't worry about this really long code cell. This is for my interactive graphic. You're welcome to look at it later. But I am going to run it. It's just a function. All right, so what is k-means? So k-means uses the expectation maximization algorithm. It's a super simple idea. So I remember I said 3 clusters, I want 3 clusters. I kind of said that in advance. I'm smart because I've seen the iris data set, so I know it's 3, right? Lucky me. So what k-means does is it will guess potential cluster centers. I believe in scikit-learn, it literally picks well, I don't think it's totally random, but I think it's fairly random given certain ranges of your data. It just plots like 3 different, points on your data, like in your data set, as you can imagine, like it guesses 3 centers. So you have these like 3 centers in your data set. What happens next is it assigns points, like your observations, to that nearest cluster. This is probably not an ideal location for the cluster, but it just goes ahead and assigns the points to the nearest cluster. Then you reset the cluster center. So you move your cluster center to the mean of those points, okay? So we're doing that with 3 cluster centers in our data. Imagine it in like 3D space. It's actually, I guess, 4D space here, but all right, oh, I'm sorry. No, it's 2D space because I did PCA, right? So I reduced my dimensions to 2. All right, so this, remember I defined my here I'm defining min and max clusters. That's for the interactive plot. And then interact calls a certain plot. So it didn't work for me, but it did plot something. Well, I must have upgraded my system. I don't know why it's not working. Maybe it works for you guys. By working, I mean this plot is interactive. That would be working. So, but what's neat here is you can see the initial state. Okay, so remember we have like one component. We have 2 components. So one component is on my x-axis. Another component is on my y-axis. So the most important one, one that explains the most variance is principal component 1, and that's my x-axis. Okay, so the way scikit-learn runs k-means, and I think this is generally the way it works. Like I said, it just plots 3 different cluster centers onto your data set in a visual way. I That's what I'm trying to say. So it assigns three cluster centers. And then what's going to happen is the points that are closest to this cluster center get assigned to it versus this cluster center and this cluster center. So it's going to basically probably tell, like, if we went through this iteration, that all of these purple ones on the right, except for maybe these guys, will get assigned to the purple cluster center. And then what happens next is those cluster centers move to the center of the points that it's been assigned to. It does this over and over and over, and eventually it'll converge. And let me just tell you, like, the result of, I don't show it because it's not working, but the result of this particular k-means run doesn't do a very good job. So hopefully I can get this working and update the code and maybe get some snapshots for you and put that on the GitHub site. But just to compare, remember our original PCA, and then we plot, here I'm actually, this is an old plot from a previous notebook. I plot the actual labels onto the data, okay? So technically, if we have 3 different cluster centers, right, and we assign that with k-means, we'd hope to get these guys as our different classes in our, structured data set here. And you're not, with k-means, you're not going to get back to the labels, right, because it's unsupervised. What's our status on the food? Oh, awesome. Okay. It looks like the bell has rung and school is out. So please feel free. Yeah, just go through the rest of this notebook. If you have any questions, come up to me or email me at some point. I think my email address is somewhere. Yeah, I'll get that to you guys. So I'm also on Slack, the Slack site. So post questions to us there. Okay, great. Thank you so much for listening.
Okay, we're gonna have a bit shorter lunch today. If you could just grab one sandwich first, and then if we have, because we do have a lot of people today and some people overflow. I do want to make 2 quick introductions. If Erin and Fabrizio could come up here. So Erin is organizer of the Women in Machine Learning and Data Science. And so I believe a lot of people here are from that group. If you could raise your hand if you are. You can see, yeah, it should be about half. So Erin, do you want to give a quick introduction for the group?
Yeah, so I actually didn't organize anything about this workshop, which was great. I just advertised it to all the people in the group, and the goal, I think, was to get like a half female, half male ratio, and it looks like we've done a pretty good job. So thank you for showing up. And then if you don't know about the group, it's just a meetup group, and we're trying to have more events in the South Bay, but most of the time we're in the city. But yeah, we're trying to do more events down here so that if you guys live around here, it'd be easier to go. And yeah, so it's called Bay Area Women in Machine Learning and Data Science, and we're on meetup.com, or you can go to wimlds.org to find out more. And there's also, if you have friends in other cities, there's one in New York and Chicago and North Carolina and probably Boston soon, and maybe some other cities. But thank you.
Cool. Thanks, Erin. And Fabrizio here is also a volunteer, and he is one of the contributors to TensorFlow. So I'd like to, do you want to give a quick introduction?
Oh, yes. Hi, everyone. I'm Fabrizio. When TensorFlow was released, I jumped ship. I say, okay, this is where everyone is going to be in a few years. So I'm particularly interested in distributed computing and GPU. So I implemented a few operations for TensorFlow that make that the life easier for those 2 words. Thank you.
Okay, thanks. Yeah, so we'll start here at around 110-ish. So yeah, help yourself to lunch.